Welcome to today's tutorial. In this session, I will introduce Auto-MISCHBARES, an abbreviation for our millimeter-scale high-throughput battery research system. This platform facilitates fully autonomous electrochemical measurements and represents an extension of our initial platform, HELAO. For those interested, I have provided a link to our paper for further reading. Before we start, I would like to outline the overall workflow of this modular framework. Initially, the operator configures his experimental setup and schedules one or multiple batches of experiments through a user-friendly interface. Once configured, the batch requests are transmitted to a Python backend via Flask, requiring no further user intervention. The orchestrator then manages the sequence of experiments asynchronously, communicating with each server in our device hub through Fast API, a web server framework. Upon completion of the experiments, the orchestrator compiles a comprehensive report detailing all measurement data, experimental steps, and associated timestamps, and deliver it to the user. Next, I would like to explain further details about the device hub. The device hub in Auto-MISCHBARES consists of several devices that collaboratively perform experiment. At its core lies a miniaturized 3-electrode cell setup known as a scanning droplet cell or STC. This setup includes a working electrode, a gold reference electrode, and a counter electrode made of platinum. These electrodes are positioned within a cell housing made of PTFE and are movable via a stepper motor from Ovis company to facilitate various electrochemical protocols. The electrolyte is introduced through an inlet which connects to a syringe pump manufactured by Hamilton company, and user can attach a tube to this pump filled with any electrolyte of choice. The electrolyte is aspirated by the pump and then dispensed from the STC head into a waste holder. To address the issue of residual electrolyte, which can lead to salt formation and measurement inconsistency, the head moves to a wiping position to remove leftover electrolyte. Subsequently, the head relocates to any measurement area on the working electrode designated by the operator in order to execute the scheduled protocol. The working electrode is connected to a multi-channel potentiostat device from Metron company via a red crocodile clip. Once all electrodes are connected, the selected protocol is executed. Furthermore, cameras are strategically positioned to monitor the quality of the experiment at various stages and to prevent hardware failure. Returning to the schematic representation, I've just introduced you to the setup. In this system, variety of quality control protocols are implemented. These include drop detection to ensure material sufficiency, verification of electrical contact between the 3 electrodes for electrochemical measurements, and communication feedback. This feedback is provided through a Telegram chatbot-based system, which informs users about the progress, status, and potential failures. As the measurement starts, real-time plotting via bokeh begins immediately, showing the flow of measurement. Upon completion, the data undergoes immediate analysis using MADAP. MADAP is our data analysis platform and comprises various classes including impedance, voltammetry, and RNEOs. It generates reports and summaries in CSV and JSON formats along with high-level visualization. For further information, please refer to the link provided in this video. After the analysis is complete, all raw and processed data are stored on the fly in our local PostgreSQL database. This database consists of various tables. The experiment table contains all general information, including operator details, date, metadata, material, and their specifications. The motor position table records the position of the selected working electrode, while the measurements table per procedure setting with raw and process data for every measurement. As demonstrated in the HELAO platform, it's possible to optimize subsequent experiments using active learning algorithm. With the addition of our data management system, this process has been further enhanced. By visiting the open source MISCHBARES repository, you can access overview information, including installation procedures, guidelines on starting the application, and database setup instructions. Additionally, by clicking documentation pages, you will be directed to the documentation page, where you can see every aspect in detail. Within the MISCHBARES sections, you will find information on all the drivers, actions, and unit tests utilized in this study, along with detailed explanations of each component. On GitHub, you can initiate your own MISCHBARES project. Here, you have the option to download or clone the repository. To clone, copy the provided link, navigate to your desired folder, open the command prompt cmd, and type the command git clone followed by the copied link. This will clone the repository into your chosen folder. Next, change the directory to the newly created folder to view all the contained files. Firstly, it's important to ensure that the database is running. The database can be handled the best with pgadmin, which should be pre-installed on your machine. Connect to your server, and once connected, navigate to the databases. This is the standard database provided with the pgadmin installation. You can then create a new database. We have named ours MISCHBARES test. To avoid manually creating all the schemas, import the backup included in the cloned repository. In pgadmin, go to the Query tool, open the file from the cloned repository, navigate to the MISCHBARES, then DB, and open the SQL file. This contains all the necessary commands for our tables. Execute these commands, and the process should be quick. To check the creation, open the schemas and tables. You should see all the tables, including procedure, raw measurement, experiments, and the user. The next step is to prepare the Python environment. This is done in a classical way. So open the command prompt, connect to the created environment if you have one, and run pip install -r requirements.txt. Now you're ready to launch the MISCHBARES app using the command python app.py. The login screen will require a username and password, which must be manually added to the database prior to the login. For demonstration purposes, I'm using a test user and password, which leads us to the main interaction board of MISCHBARES. In the UI, you can import general information about your substrate for experimentation, such as material, electrode number, area, concentration, and motor position, as demonstrated in the device hub. Let's input some default values. For motor positions, there are two options. If you have specific points of interest, you can input them by setting XYZ coordinates. separating multiple points with semicolons. Alternatively, for a symmetrical substrate, input the number of rows and columns, the height for the motor that needs to go down, and the number of points in a row. Then click on Generate Mesh Grid to produce all required motor positions. Finally, specify where the result should be saved and click Save. This will create your general settings. Next, we move to experimental setting. This app allows for multiple batches of experiments. First, define the number of batches, which you can view in the window. Additionally, you can specify the number of experiments in each batch. The UI will react accordingly. Configure the settings for each experiment or use the default values provided by HELAO. For experiments, select from variety of electrochemical protocols available in the list or add a custom one in the Autolab procedural script. Once you choose an experiment, all settings and values for that specific protocol will be available. For example, in cyclic voltammetry, you can set the start, upper and lower vertex, number of stop crossing, and optionally start at the open circuit potential value. After defining everything, click Save Batch Settings. All JSON files defining your sequence of experiments will be saved. Now simply click Run HELAO and it will execute the sequence for you. It's now time to take a rest. Let's proceed with a demonstration. We will open the app using our test user. And then, for simplicity, I've just used default setting. Let's choose a single measurement. In this case, I chose EIS. And then save the experiment. After clicking Run HELAO, the process starts in the background. You will observe various components being added, representing the different machines connected to the experiment. HELAO will wait for all servers to be ready, sending out health requests every few seconds. Meanwhile, you can review the configuration you created via the UI, including batch numbers, the experiments, and the general config. Once all the listed servers are ready, the program begins. One of the first steps is to start the live visualizer, which is used to oversee the automated experiment. You can choose the X and Y axis you wish to observe. The experiment will then start. For instance, with EIS, you will see the frequency range from 10,000 to 10 Hz. Let's take a look at the Nyquist plot. Here, you can monitor the progress until it's completed. Once the measurement stops, the data is processed through Modular and will be saved for you. In the HELAO folder under Tests and then Data, you can find all the data saved on the fly. The JSON file parsed from Autolab, the potentiostat NOx file, and the configuration are all there. In the EIS folder created by Modular, you will find the process data and all the visualizations. As mentioned at the beginning, all data is also saved in our database. Let's take a look at here. Here is our EIS procedure with its configuration saved. You can open it and see all the details. Simultaneously, all the raw data is stored here as well. Each procedure and raw data ID are unique, so it would be easy to retrieve them at any time. This was our database server. Finally, I also wanted to show you that our initial HELAO server keeps track of all the metadata and every step along with their time steps, which are saved here. The EIS example is just one of the many options available. For instance, I can run a chronopotentiometry experiment to demonstrate. The process is similar, and you can always access all the saved data. Other procedures follow the same format. For the sake of time, I created some examples for you, like cyclic voltammetry measurements, their data, and the plots created by Modular, as well as the CP experiment we just ran. You can continue with any procedure that interests you. Now I am going to demonstrate one of the quality control measures that is implemented there. Once all devices are initialized, the experiment begins. You will notice in my PowerShell that the motor moves to the waste position. It then attempts to pump some material. A video automatically pops up, displaying a green frame indicating the region of interest. The frame is used to detect motion using the OpenCV library. As you can see, we observe no material present. As I earlier mentioned, in Auto-MISCHBARES, the communication happens through Telegram chatbots. In this scenario, a message is sent to the user indicating that the bottle is empty and requesting the user to refill it if no spare material is available. For this demonstration, we have set a waiting period of 1 minute, although typically it sets to 2 hours. The experiment remains on pause until someone refills the bottle. After the waiting period, the machine attempts to pump material again. During this waiting phase, the orchestrator will be set on the pause. Let's observe a 1 minute timeout here. If after the timeout no material has been added, you will see that the orchestrator closes the experiment. This is to prevent any unreliable measurements from being conducted due to the absence of electrolyte. Now I would like to demonstrate all the steps at once with a real working electrode rather than a dummy cell and explain the remaining steps for quality control assessment. Initially, I defined one batch in which I plan to run 3 electrochemical impedance spectroscopy experiments. After clicking Run, we wait for all servers to be ready, monitoring their health status until the visualizers pops up. As you can see in the video, the motor first moves to the waste position, begins to pump the electrolyte, and simultaneously the camera starts checking for material sufficiency. In our region of interest, the camera detects the discharge of materials. Having confirmed this, we then move the motor to the cleaning position to address any residuals on the scanning droplet cell that might cause measurement issues. The motor wipes away all the remaining materials. Next, the motor moves to the pre-selected position. Here you will see another aspect of our quality control assessment. The motor moves downward very slowly to avoid applying a sudden force on the substrate. During this process, the potentiostat continuously measures the potential until a sufficient electrical connection, as defined in our configuration file, is established. This is to verify whether we have made contact with the working electrode. Once the connection is established, we wait a few seconds to ensure stabilization and to confirm that the electrode has sufficiently soaked the electrolyte. Then the measurement begins. Once the measurement is completed, the operator receives a notification and it will be kept informed. Afterwards, the motor returns to the wait position to dispense fresh electrolyte for the next experiment. All the steps will be repeated until the defined experiment cycle is completed. In our demonstration case, we run the sequence 3 times. Once completed, the operator will receive telegram message. The motor will then return to the home position. The orchestrator will terminate and all the information regarding metadata and measurements will be available in the data folder and our database. That concludes the demonstration and I hope you enjoyed it. Thank you.